Well, first, I just want to thank everyone for coming from faraway places and some not so far away. It's really thrilling to have everyone in the same. So, I thought what I would do in my remarks is use this as an opportunity to look backward at the origins of this enterprise, try to just briefly summarize, and maybe I'll be able to do it, maybe not. What we've learned since it began, and what still are things that are to be learned, or things that I guess that's what it comes down to, things that I would still like to learn. You can make your own decision. So, looking back, this is a picture of my colleague Captain Broman, picture circa 1985. And the origins of this enterprise were around 1983. Kathy and I were talking about a number of things related to this time. We were walking also on a beach, and that's kind of part of the reason that we're here. I mean, some sort of ask, why are we here? Not why are we together, why are we here? And this was a kind of favorite spot of hers. This was not the beach where, I still remember we were walking on the beach in Milford when we came up with the name for this enterprise. And it was like, I can't actually even remember which of us came up with it. It was like we were kind of making various approximations, and finally, oh, that's it. So I want to look at what were the issues at the time that gave rise to this approach, and what were the key ideas that articulatory phonology developed to address these issues. And I use the word developed there very carefully. I'm not convinced that any of the ideas were ours. By ours, I mean mine or Kathy's or Elliot's, but they were in the air at the time. And I think if anything, what the enterprise did was we created a sort of coherent, or I like to think coherent, framework in which it was possible to ask questions in a systematic way, including a computational simulation of that framework in which it was possible to really ask questions. So yeah, in the years since, what we learned about phonology and about speech using these ideas, and what might we continue to look forward to learning. So we go back to what the problem that was seen at the time was the apparent incompatibility between phonological and physical descriptions of speech. And movie, phonological description of speech is a sequence of symbols from a small inventory that recombine to form words. And the physical description is continuous context-dependent variation in many parameters. Few of them shown here. And really, I think the person who put this into focus originally was Carol Fowler, both in her dissertation and paper in 1980, with some others on her own, and specifically contrasting the properties of phonological units and physical measurements: discrete continuous, time invariant, time varying, etc. Now, historically, I mean, basically, Pocket talks about this idea, talks about this incommensurability as well. The incompatibility is kind of resolved, in quotes, in Pocket and other places by completely separating the cognitive and physical descriptions. And what was in the air at the time, around 1980, was, well, that just pushes back the problem. And you can say that this is cognitive. Why are they related at all? What is it about these bodily movements that means they're going to have this kind of cognitive structure? These, I think, are, for me, what the key components or ideas that were articulatory phonology put together with respect to resolving this. Dynamical systems representation, which really those follow-up papers I mentioned were the first ones to explicitly make that connection, and for her that was the key to this resolution, as well articulatory synergy representation, and the other piece, which was the potential breaking segments down into subsegments that had their own life and could overlap in various ways. I'm actually going to start with that, because for me, and for Kathy Broman at least, that was historically prior. That's kind of where we started. And so the idea was that, unlike, I mean, we were sort of still thinking strictly in terms of speech segments, even in production at that point. And in the era at that time was the idea that in the relatively invariant sub-segmental articulatory units, which eventually became gestures, with their own temporal extent, could overlap in various ways. And those different temporal alignments could do various things, and the misalignments could have phonological consequences. And these ideas were floated, so to speak, through the icebergs of Osamu Fujimura, who was writing about it that way in the early 80s. And Kathy was working with Osamu at the time. Mary was around there at the time as well. And that was the basic idea. And Osamu's idea is you have these fixed things that kind of float in a sea of phrasal space without sort of more understanding of what's involved. And Kathy had been developing a demi-syllable-based speech synthesizer called Lingua. But as part of that, the set of synthesizer rules explicitly recognize invariant articulatory units, and the rules express temporal overlap. And clearly there's also some relationship to autosegmental phonology, which was developing at the same time, though the game there was somewhat different, but it was really getting at the same phenomenon. So this idea of subsegmental units, I'll start with what have we learned about that in the course of time? So yeah, subsegmental units, now gestures, don't float freely with respect to one another in sort of free phrasal space, so to speak, but they're coordinated to one another in phonologically specific ways. So the grammar is in that coordination in some ways. That's something we learned. I'll talk more about that. And the coordination may involve synchrony in some cases, or sequentiality or other possibilities. And what made this powerful is that what we learned is that the organization, and it is a phonological organization of segments, of gestures into segments per se, is not a good predictor of what kind of coordination you get. But syllable organization is. So gestures belonging to a sequence of segments may be coordinated synchronously. An example here of someone saying "to back," and the lip gesture would be and the vowel gesture would be begin at the same time. So there are different segments beginning at the same time, whereas conversely, gestures belonging to a single segment can be sequential in time. So here's the tongue tip and tongue body gesture in the N in the O. This is Danny Bird's work and some others. And they're synchronous when they're in onset, but they're sequential. So that was one thing that was learned. And the other is that variation at the boundaries of words and syllables, there can be variation in temporal overlap at what was at the time called relatively fast speech rates. And those overlaps can produce what we traditionally treated as phonological consequence, so perceived assimilations or deletions. Danny Bird was also kind of in that area and showed up at Yale as an undergraduate and worked, I think it was the first actual perceptual experiment with the computational model that we produced, and showed that the changes in overlap can produce assimilations and deletions. And this is some familiar examples of data that Martini collected a few years later. And kind of, though we didn't talk about it that way, going back to it, it sort of also starts to reveal the important role of prosody in these overlaps, which is not something that originally I at least thought about at all. I never thought about prosody in those days. So here's the phrase perfect memory being
She had a perfect memory for details.
So it was described as carefully articulated, but there's clearly some kind of boundary between perfect and memory, whatever that boundary is, which is absent in.
She had a perfect memory for details.
In this case, you get more overlap of the lip gesture with the tongue tip, and the T, well, is it there or not? It certainly the T disappears. And spoken more quickly.
She had a perfect memory for details.
You also get some reduction in the magnitude of the gestures. just specifically related to prosody some years later, took some examples of X-ray microbreeding data where we had a project to do a boundary transcription of that with Jennifer Cole and Ayuro Katsuko actually ran the transcription stuff, and Mark Keating. And so here's an example of the phrase told before, where 11 out of the 38 transcribers heard some boundary between the told and the before, and you can see clear release and the D is obvious. But in the case of this, where only 2 transcribers hear a boundary, there's much more overlap and no D release at all. And we tended then to simulate those 2 productions using the computational model, which again I'll talk some about its development, and to add a boundary slowing gesture, high gesture, in one and not the other, and indeed we were able to simulate the emergence or not emergence of the actual release of the D just as a function of the strength of the solid boundary. So all this is stuff that we've done. Other things, so there was an early hypothesis, for example, that all post-lexical assimilatory alternations arise from systematic changes in overlap and reduction of gesture magnitude. Nothing else happened besides that. And always good to take a strong hypothesis, and always good eventually to see what kind of data actually falsifies. In this case, it was a dissertation led by Honoroff on including place assimilation in Spanish, and we had very good examples of people reading sentences like digan caja alto and digan caja alto, and the final N in digan clearly assimilates to a following labial dorsal, but it first of all, it completely disappears, and the length of the labial or dorsal gesture decreases. You can't describe that as any kind of change. There's something else. I still don't know exactly how I want to think about the dynamics of what's going on in these cases, but it's not overlap at the same place. Another direction that again clearly exemplifies how the coordination relations really needs to be part of whatever grammar is these days going forward. Work by Dionys Kathos on Moroccan Arabic, who showed that coordination per se plays a critical role in the phonology. So this is one version of this was an early paper in 2002 and a recent soon to appear paper in NLT, and revisiting it with real articulatory data. And so what he shows is that stem affix junctures, so Moroccan Arabic have both stem affix morphology and template morphology. The stem affix juncture sequences of homoorganic consonants are coordinated with partial overlap and therefore no release. But in morphological templates, homoorganic sequences are coordinated with no overlap, so completely sequentially, such that there's always release. And that's a systematic difference between those 2 morphological types. Also, and this is kind of a lot of the material in the earlier paper, the constraint for templates conflicts with what is otherwise the preferred coordination in templates, which is partial overlap. This is a case showing the tongue tip and lip partial overlap in a templatic sequence, DB. And so that conflict between what's required of the homoorganic ones and the heterorganic ones plays out in a variety of ways in the grammar. So from this relatively, in one sense, narrow perspective, looking at coordination in grammar, what are things that I would still like to know? Well, one is how can these distinct abstract coordination patterns formally be characterized within a dynamical model? I mean, it's easy to look at these and say they have partial overlap, but what is that? What's actually being controlled there by some dynamical model? I don't think any of the existing models really do a good job of that. So what actually would be the difference in the grammatical and the dynamical model in for those different patterns of Arabic. And also, I mean, there have been a number of studies showing systematic language differences in the degree of overlap systematically in consonant clusters within words and crosswords. Russian and Georgian, little or no overlap. German and English, partial overlap. Cantonese, almost completely overlap. What regulates that? And why do you get those possibilities and not a lot of in-between ones? So there's a lot there. Also, I think the various studies have shown that in consonant sequences, when the first one is produced anterior to the second one, that there's more overlap than in the converse case, with more back one is produced first. And I don't understand why. A lot of people talk about why. Recoverability, for various reasons, I won't get into, recoverability doesn't work. But I think, I mean, I have the intuition that this asymmetry is telling us something more basic about the kind of spatio-temporal organization sequencing. The spatio-temporal as opposed to temporal aspects have been, I think, grossly understood. Other directions are the relationship between the segment internal gestural coordination and phonotactics. So, recent paper by Rachel Walker and Mike Proctor started to look at that with respect to liquids, but I think there's a lot of other relevant material where the actual internal structure of segments interacts with what is traditionally the segmental phonotactics. And finally, the whole issue of segmental timing has made a reappearance if there is a mainstream phonology world in what's called Q theory, among others. Okay, the next point is to look back at the principles of just the use of dynamical systems at all to represent these subsegmental units, which is relevant really to all of these issues shown here. So what's important here? So dynamical systems, just the briefest of interviews, introductions, kind of the way Bill and I do it for our intro classes. There's two parts to any dynamical system. There's the state that you're modeling, that is the quantity that's changed over space or over time that's being described. And then there's the law, right? So the law holds everywhere in space or time. And the critical aspect of all of this is that the law is fixed while the state is changing. That's really all it is about. This the plot there shows a very simple first order system. The change in x is equal to -0.5 times the value of x. And you iterate that, and you get exponential decay towards 0. And the idea behind all of this is that if phonological units are dynamical laws, then the time-varying and time-variant aspects are lawfully related. The law is time-invariant, the actual the state changes over time. As well, you can relate it to context independence and discreteness. So the same context independent law will give rise to different context dependent continuous time functions as a function of initial conditions. All the conditions shown at the bottom. And also all those initial conditions eventually wind up with the same value. So the system in some sense can be described as seeking a goal or producing a state in equilibrium or an attractor state. So time is continuous, but the attractor in some sense is discrete. The same law always has the same attractor, even though in real life it may not actually get towards attractor if it's not active enough. Okay. So, and again, as I said, Califano was the first to see that defining phonological units as a dynamical system could solve the problem of incompatible descriptions. So Phonological units are laws with fixed independent parameter values that are context independent. The phonetic state corresponding to a phonological unit evolves over time, continuous context. The critical aspect is that the phonological structure, that is these constants, the goal, which is C over K, and the stiffness, which is K, if this were a simple first-order system, these, the ones in red are the phonological constants, and these are the phonetic consequences of that. These are the actual movements in space and time, and so the phonological constants and the phonetic quantities are actually in the same equation, so they're not mediated by something magical. So what have we learned with respect to dynamics over this time? And there's really several different areas. I'm just going to touch on a few of them. One, just for gestures themselves, the dynamics of real-time production of gestures. So we learned that sort of, well, that at least an adequate reproduction of intelligible speech that mimics some signature properties of speech is feasible, possible by modeling gestures as critically damped second-order systems in the task dynamics model. That's the basis for the computational system that we developed. And that some examples of allophony can be modeled through, particularly phonologically regulated allophony through undershoots. So cases where gestural activation is shorter than time to reach the target, we get some reduction. And Ben Carell did some work on spiratization in Spanish that shows it's possible to really derive its properties systematically in that way. And in recent work by Sorensen and Gaffos, has gone back to an issue that actually Elliot and Kelso looked at a long time ago, which is the possibility that really gestures should be modeled with a nonlinear soft spring equation instead of linear spring equation. But really, dynamics has sort of sprouted many heads in the time since and been used for much more than modeling gestures. So one subheading would be what we call dynamics of gestural planning. And in this case, the critical idea here is that when we look at nonlinear dynamical systems, they have multiple attractors. And once they have multiple attractors, they can do various things that are related to what we call contrasts that can be associated with these different attractor states. So the work I did with Elliot and Goldstein was here. We developed a notion of planning oscillators that can be represented in a coupling graph and can account for robust observations about intergestural timing as a function of syllable structure, and also the variability of that relative timing. So in this view, onset and nucleus gestures are coupled in phase, nucleus encoded gestures are coupled antiphase. Multiple gestures in an onset, for example, are also coupled in phase, which gives rise to something called the C-center effect, which has been used a lot in many studies over the last several years as a kind of diagnostic of syllabification, and also with respect to integrity of speech in the locus of problems in various speech disorders. Kind of a related but somewhat different model is Sam Tilson's competitive cueing model, that the selection part of the selection coordination model. Competitive cueing is a different kind of dynamical system. And in combination with the coordination part that he's argued can account for a variety of aspects of phonological structure, and this gives moricity as an example. And finally, in certain examples, you could use these multiple attractors to account for qualitative changes as a function of changing some continuous parameter in the speaking context or possibly in the grammatical context. So the gestural intrusion speech errors that were investigated a lot by Marianne Coutier and I could be that kind of dynamics and phase transition can be involved there. Certain discrete alternations. And Ben Carell did an example of switch between pre-aspiration and post-aspiration in a dialect of Spanish, Western Andalusian Spanish. And going back some years, issues of resmodification. And finally, direction, and I think David Deese's talk will say more about this, what we call grammar dynamics. So the shift between attractors is a function of biasing parameters, which can be other grammatical parameters, can account for both discrete and continuous aspects of phonological alterations. And an example of that is the count of harmony in Gauss and Denish, and kind of handout of John Goldsmith's that I eventually recomputed, showing a kind of coupled oscillator analysis of these threads. Dynamical systems going forward. Well, there are these production, both these sort of oscillatory planning models and production models, but the question of use of feedback isn't really well handled in any of this. I mean, Sam's model has a bit of use of feedback and knowing when something is done. But I think there's more than that. And so the question is, how does feedback, I mean, all of us, I think, acknowledge that feedback ultimately is important, just never keep it in. How does feedback of various kinds modulate ongoing planning? And the other aspect that I think is ultimately related is that planning models really are purely temporal. They're not spatial temporal. We don't care what the gestures are. It's just like you've got two gestures, you've got to coordinate this way. That's not right. Again, we've always known that it's not right, but you take big steps. So, I mean, a good evidence where it's not right is that the example of syllabic constants. And I've looked at some in Tashkent Berber, and Mariana Kuplia has a good evidence of that from Slovakian, where, well, you get a syllabic consonant nucleus. It doesn't show the onset nucleus synchrony that CB syllables do. And again, related ideas is the role of sonority in syllable structure, completely missing from modern syllable structure, where it's just about time. Okay, so the last point is the articulatory synergy representation, which sort of was key to relating the low-dimensional and high-dimensional descriptions of speech as well as context mechanisms. And again, showing up, Kathy and I showing up at Haskins around the time that there were all these ideas going on produced by people like Kelso and Betty Teller, and Elliot, of course, who was really key to developing the levels of task. And of course, the basic idea is that the performance of any skilled motor task requires the cooperation of several independently movable body parts or articulators. And there's a large, possibly infinite number of postures that will do the job, and this is sometimes called redundancy, but when we learn to perform a task, part of what we learn is the pattern of dependencies among articulators and performing the task. And that's in various over the years called a synergy or coordinated structure, or more recently control. And so the synergy allows the task to be performed in different ways, in different environmental contexts, by different actors. So with respect to phonology, the idea that we developed was the gestures are motor tasks developed performed by a set of articulators to achieve the goal. And the model assumes that the basic dynamics are defined at the level of the task. The dynamical system produces time-varying behavior of the task variable, but then is distributed across the set of articulators belonging to that synergy in a context dependent. And all that is the basis of the model that we developed. Kind of what I'm focusing on in the rest of what I'm going to talk about is, well, what are the spaces or tasks of the gestures that are specified? And there are various candidates: auditory properties per se, acoustic properties, aerodynamic properties, vocal tract constrictions. And possibly different gestures can have different task spaces, or as I say again, maybe the gestures can have task descriptions in more of one of these spaces at the same time. The hypothesis we took at the time, for reasons that I'll go into at the moment, was that the tasks are constrictions of 5 different effector systems, ellipse and time tip and time body of the device. And so basically, for example, location and degree of constriction of the tongue are 2 task variables related to a set of articulators that we could control using the articulatory synthesizer movement. Phil Rubin at the time was in the process of making, sort of harnessing Mermelstein synthesizer to make it usable. And thinking back, I think there were really at the time these 3 motivations for constrictions. We're assuming that constrictions were the task. One was, well, in the end, constrictions are a major determinant of the acoustic properties, so you're kind of getting 2 things for 1. The other was just pure utility. So the task dynamic model needs to know the forward map to do its work. The forward map relates a vector of articulators to a vector of task variables. And we also need to know the Jacobian, which is the matrix of partial derivatives between the task variables and articulatory variables. And the idea was, well, given the simplified geometry of the articulator model, we could get those analytically. These are still the days, it was still near the beginning of this. It took a long time to compute anything. Right? So we weren't going to easily get the forward map to the acoustics in anything like real time. So it's like, no, we're going to go with this. And finally, I think I'd like to call it locality. So the point is, given the work we're doing, because of the lawful relation between phonological analysis, as we were presenting it, or thinking about it, as a structure of gestures and the resulting vocal track movements of the sound, it actually was possible to test phonological hypotheses, or hypotheses representations of particular utterances using quantitative data. I think that was something novel. There was really, as long as the relationship is lawful, you could say, well, have this representation, the data should look like this, but it doesn't, the representation is wrong, it's wrong with this framework. But it's only possible with an explicit model that will go all the way. And that was the model we started to develop then. It was called Just at the time, and eventually we morphed into something called Tada. And it allowed us to test various, and other people, various hypotheses about assimilation, deletions, temporal control, or lack of it, targetlessness, ultimately, syllable structure, and it had these components, a model that specified what the gestural structure is for given utterance, and represented it in terms of a gestural score, which is input to the actual task dynamics model that produced time movements of the articulators over time, and eventually something here. It probably said something about it. It said math, that doesn't really matter. The key idea was this representation of gestural score, not just help visualize this information about the structure of gestures, and show that gestures have extent in time. Of course, the actual phonological representation had to be somewhat more abstract than that, because these are actually in real time, and that won't do. But just looking at it allowed us to learn a lot about the relative timing of these pieces and what they might actually look like. And representing contrast in gestural scores, can see very clearly one utterance has a gesture, a particular set of task verbals that the other lacks, which is intrinsically discrete. Contrasted parameter values, like for soft versus fricative, and the temporal organization of gestures. And by locality of constriction tasks, I mean that constrictions are produced by effectors that are local somewhere within the vocal tract. And so because the constricting organs are partially independent of one another, so the lips and the tongue tip are partially independent, the dorsum of the tongue and the tip of the tongue are partially independent, it means that actions of these different effectors can be co-produced with minimal interaction, which allows the parallel transmission of information. so in this case, you can see tongue tip constrictions being produced while the vowel context is, the tongue body is really taking on the shape of the co-produced vowel. So there's a way of at least seeing, and I guess visualization kind of important here, seeing that more than one thing is going on, and that is appealing. In contrast, the acoustic properties of the vocal tract are global, so they're depending on everything that's going on at any given time. It's certainly possible to analyze the acoustics into the components that could be accounted for by the separate parts, but again, looking simply at it, it's easy to visualize in terms of these levels. So I have a lot to say about these in slides, but I'm not going to get through them. But I will just go through what I see when I say what have we learned about tasks. There's various evidence, in fact, surprising evidence to me in some cases, evidence supporting constrictions as tasks, and other evidence supporting other possible task variables. So among the things supporting constrictions were work by Khalil showing that constrictions actually can be specified by former frequencies and amplitudes. That if you know the former frequencies and amplitudes, you can actually predict constriction location and degree pretty well, at least in the, as we get it in the extreme microwave. And somewhat related, but not exactly related, work by Osani and Vikramitra, showing that constriction information contributes to automatic speech recognition. And I'm not going to go through all these slides I have for this. This is part of the work that we had with Elliot, and it was a graph with Jennifer Cole as well. And but what they found was that if you learn the extraction of constriction task variables from the acoustics and then added that to the MFCCs with a straight up HMM recognizer, in noise, you could improve a lot by as much as, you know, the percent correct at reasonably high noise levels improve as much as 35%. And the question, well, why does it even help? I mean, it's all the same acoustic information. It's all starting from the MFCC. So the hypothesis was that specifically the task variables are places, there's lots of information in acoustic signaling. Acoustic signaling is extremely rich. Speech recognition wants to know about, is this a P or a B, or this is a T or P? And so the task variables are specifically telling you something about contrast. And so that's sort of projecting the huge dimensionality of the acoustic space onto that set of dimensions that's relevant to contrast by system. And the last piece is that cites recent work out of in Chang's lab, Josh Chartier is the first author, cites in the motor cortex during speaking show, if you kind of look at their encoding, encoding or decoding, I was getting very confused with this stuff. Anyway, they had, using ECOG, they had people speaking and created a really excellent model going from acoustics to pseudo-EMA trajectories that gets remarkable results. Sort of about 65, correlations 0.65 for untrained speakers. So they actually could show that when people are speaking, that sites in the motor cortex are the best encoding of them is coordinated movements of the articulators to perform different constrictions, labial, coronal, and dorsal constrictions. Some stuff for vowels that's a little more confusing, but those three constriction types very clearly represented by distinct coordinated patterns of all articulators. So that much better results than either attempting to encode phoneme identity or phoneme frequency identity or phoneme frequencies or individual articulators. And there's some related work from Emily Lugler that you've been part of as well. And it supports the same idea that in the motor cortex and even in the IFG part of Broca's area, there's gestures are better coded than segments, although the difference in the Broca's area is not as large. But there's also evidence supporting other task variables. So there's lots of roles of use of auditory information in speech production. So work on sensory motor adaptation and also what's called the speech-induced suppression, where you get reduced firing auditory areas when you produce it rather than listening to your own speech. So there's something about expected consequences of your own actions that percolate down to the evidence from Guthrie's lab showing lower F3 as a goal of art production. And the evidence is pretty good that at least across all subjects, the most common way of understanding the variability in art production is to say that it sort of minimizes the differences in F3 or maximizes the lowering of F3. That much seems pretty clear, even though you also see effects at the level of task variables of constrictions, but they don't work the same for different speakers. And finally, while one might think that we've known for some years that the patterns of activation in the motor cortex during listening, which were discovered about 15 years ago, might say something about also the use of constriction information in speech perception, which after all, if we're talking about phonological units, they should show up in speech perception as well as production. But it turns out, interestingly, if you look at what looking at how you can predict the patterns of firing in the motor cortex during listening, they're very different than the patterns during actual speaking. And just want to see if I can quickly switch through some slides. So during speaking, you get, well, this is really the relevant bit here. So if we look at, these are sites in the motor cortex, and here's a site that is during speaking, active during D and not a G, not D or G, and one during D and one during G. But notice none of those, there is any firing during listening. Those are representing the listening activations are in red. If you look at cases that are active both during listening and speaking, there's no difference across constriction. And the overall clustering of the ability to predict, or the scale, looking at multidimensional scaling of the firing patterns reveals that it's still auditory coding that happens in the motor cortex. And so, just going to skip going forward if I can quickly find it. I want to stop. So task space going forward. So I think forming frequencies and constriction somehow, or something like forming frequencies or auditory properties, should both be part of the task space. What does it mean for them to both be part of the task space? I'm not sure. But you can figure out what that means. And there also clearly needs to be aerodynamic goals for things like acoustic sources. And that's not part of this, really part of the model at all. So pressures and laryngeal tension for F0 related uses of the larynx, and actually Richard McGowan and Elliot produced a task dynamic model of that years ago. It's never been fully incorporated into the rest of the work. But other aerodynamic goals for voicing, for turbulence, and for intensity. We know that intensity per se, apart from net zero, is relevant to prominence, but that's kind of a separate task variable from any other aspect of the use. And the problem that I've always kind of fought with since the early part of this work is, since these goals, including form and frequencies, may result from the action of more than one of the subsegmental units or gestures, it needs to be some kind of hierarchical organization of gestures into some larger global units of some sort in order to define such goals. Because the question is, I mean, segment would be the natural way to go. Well, if you want a hierarchical unit, gestures are composed of segments are composed of gestures. The problem with segments, though, is that the gestures composing them are often not synchronous. And so the key problem I've always had with this, and someone will come up with a solution, and probably won't be me, is when do those more global goals happen? When are they active in the system? Gestures don't tell you when. The segments don't tell you. What is the thing that tells you when these more global things are active? And it was kind of a problem that actually Kathy and I became faced when we wrote the large article in 1989, where we presented an analysis of constriction degree and even of sonority as sort of percolating up from the lower levels of the tubes to the higher levels of the vocal tract. But the problem with that still was, well, when is this calculation? What are the things whose properties have these higher level constriction degrees? I will wrap up actually with a point about work I've been doing recently, which is to look at this sort of a partly orthogonal approach to this, which is looking at the articulatory and acoustic binding problem, which is, if you're using auditory information in speech production and the representations, even in the motor cortex, are so distinct between the auditory and the motor representations, how do you relate one to the other in order to say, well, this segment was wrong here. Where do I make an adjustment in order to fix that? And if the representations look totally different, how do you know where you are? How do you align those representations? And just to summarize really quickly, I've been looking at attempting to find the answer to that with an old friend that Phil Wu would harp on all the time. The answer is it changed over time. Which is, yeah, the representation is distinct, but something about how they change over time must be systematically related to other. Well, how systematically related? Well, that's something I started to play with. It's looking at defining gross articulatory and acoustic modulation functions, how the sum of articulator motion over time, sum of articulator change over from frame to frame changes over time. So producing a modulation function of the picture mechanism and a modulation function of the same sentence with respect to their MFCCs. And it turns out that you end up with a sequence of modulation pulses. And two things about them. Well, they turn out to be quite correlated if you look at the modulation pulses of the picture mechanism and the modulation pulses of the acoustics, the MFCC. They're not identical, but they're highly correlated, and they have repetitive structure, and the repetitive structure is shared between the two. And not surprisingly, there's something about this that tells us something about syllables as well, because for CV syllable, we get one of these modulation pulses per syllable. And if there's a coda, we can, in some cases, get an extra one. So just some speculations about that. So modulation pulses could provide these kind of temporal anchors that I'm looking for with respect to higher level goals. They are someplace, some kind of dynamics on something that can be referred to independent of particular gestures. And they also provide a spatiotemporal basis for a syllable structure. And so to be highly speculative, let's say that gestures actually are coordinated in such a way as to optimize a 7 to 9 hertz alternation in kinetic energy, which is really what these functions are, and entrained in that way to neural oscillators like theta. And such things might, could account for why we synchronize on some consonants and vowels. Synchronization produces a single maximum of kinetic energy followed by minimum. And syllables obeying sonority sequencing should have a clear modulation peaks associated with minima, whereas if you don't obey sonority sequencing, you're going to get a lot of little chunk peaks. Anyway, this is all made up. This is stuff I'm thinking about at the moment. And finally, I left out prosody largely. There's been very important contributions with respect to things like pi gestures, which really enabled us to make predictions about, specific predictions about the effects of a particular aspect of prosody that weren't possible before. And I left it out largely because it's going to be a separate talk on it, right? And also work on coupling of oscillators at different levels of the hierarchy, the prosodic hierarchy. We can do things like polysyllabic shortening, for example, and differences in stress time versus syllable. Okay, so I've talked too long, but I knew I would.